Welcome to my presentation. My name is Shahvez Asif, and my research was about exploring a nanomaterial called carbon quantum dots and how they can be used to make smarter, more sustainable packaging material. So currently, a common polymer which is used for packaging is polyvinyl alcohol, or PVA for short, and it has many useful properties. It's biodegradable, water-soluble, and it is non-toxic. However, it comes with its disadvantages. It's highly flammable, doesn't provide UV protection, and has a limited thermal stability. My research focused on making these materials more fire resistant, in other words, increasing PVA's flame retardancy. Now, in order to help me do this, I use something called carbon quantum dots, or CQDs for short. So, what are they? These are small carbon semiconductive nanoparticles 10 nanometers in size. They are fluorescent, conductive, and environmentally friendly. I actually made these in the lab by combining citric acid, water, and paraphenylene diamine. However, these can be obtained from e-waste and biomass. So essentially, you can take literal garbage and make it into these useful nanomaterials. Now, when we were making them, something interesting happened. We were expecting their structure to be like spheres, because they're dots. However, the microscopic image revealed that the CQDs actually had a sheet-like structure when they were made using paraphenylene diamine. We got something which we were not expecting, but we decided to still use them. Maybe they could be useful. So we took our carbon quantum dots and combined it with polyvinyl alcohol to see whether CQDs can improve their flame retardancy. Now, in order to evaluate that, we ran a limiting oxygen index test. This tells us the percent of oxygen needed for a material to sustain a fire. Now, ambient air already has 21% oxygen, so we want materials with an LOI greater than 21%. So from the chart on the right, you can see how pure PVA has an LOI of 19.85, meaning it can burn in normal air. Now, when we add 10% CQDs, we saw a jump to 26.1. We compared this to a widely available filler called GNP, which is also used in flame retardancy applications. We saw how 10% GNP in PVA gave us a lower LOI as compared to 10% CQD in PVA. So our carbon quantum dots perform better than a filler which is widely available in the market. But we decided to play around some more and made a hybrid sample containing both CQD and GNP and got our highest value of 29.48, meaning this material can be classified as self-extinguishing. This also suggested that these two fillers have some type of synergistic effect. They work together to put out the fire somehow. So great, we managed to improve the flame retardancy of polyvinyl alcohol, but we wanted to understand how these fillers actually helped. We could see from the samples that all of them formed some type of char which helped put out the fire. How did that char help? Well, the char helped separate the heat from the material. It acted like a barrier protecting our sample. It also limited the amount of oxygen which can enter. Oxygen, as we know, is an ingredient for fire, so less of the ingredient means less fire. Cool. Let's dig deeper though. Let's see what is happening inside the char. We're going to be investigating the char made from our hybrid sample. This way we can see how GNP helps, how CQD helps, and how they actually work together. So pretend this is our char and it only contains GNP for now. So each material also contains volatiles. These are molecules which are inside our sample that try to get out when the fire is happening to keep the flame alive. Now, GNPs make it harder for the volatiles to reach the fire. They can even trap some of these molecules. So essentially, by adding GNP, we have created a maze with some dead ends. Now, adding CQD complicates this maze even more. More molecules are having trouble reaching the fire, and even more are now getting trapped. Remember that our CQDs had a sheet-like structure, and that is why they are represented as rectangles, and the reason why they are trapping these volatiles. Another bonus effect that they provide is that they have a bunch of functional groups on the side. Thanks to the heat from the fire, these decompose and can form water which dilute the oxygen in the sample and also provides a cooling effect, further suppressing the fire. In conclusion, CQDs can improve PVA and flame retardancy applications and can also be used with other fillers, opening the doors to many combinations. They're eco-friendly and sustainable, and we saw how they help put the fire thanks to a char with a torturous pathway, and how they can help dilute oxygen thanks to the functional groups they possess. So, CQD PVA composites show strong potential for safer, more fire-resistant packaging material. Thank you.